Okay, so this is the second lecture of the Riemann integral, and in this lecture we will start with the theorem. So let us see the theorem first. So wait a minute, guys. So theorem 1. Let f be a real valued function, which is bounded, defined on any closed interval, AB. Let us name this interval as I. Okay, and P be any partition, and P be any partition, and P be any partition of this interval I. Okay, then we have point number 1, the lower Riemann sum over this partition of the function f is always less than equals to the upper Riemann sum of this function f over the partition P. And the second point is another inequality given as the greatest lower bound of the complete function, which is given as small m. So m times b minus a is less than equals to LFP, which is further less than equals to UFP, which is further less than equals to m times b minus a. Okay, so this is the theorem we have, and we will be proving this theorem. Proving this theorem is quite easy. Okay, so let's check the proof of this theorem. The first thing which we need to understand here is that we have already discussed it in the previous lecture, that for some IR interval, okay, which is x r minus 1 to xr, you have small m subscript r given as the GLB of f over IR in IR, and capital MR is the LUB of f in IR. Clear? We have discussed this in the previous lecture. Okay, so the greatest lower bound of the function f in the interval IR is small mr, and capital MR is the LUB of the function in IR. Clear? And we had also discussed it that you have small mr always less than equals to capital M. Now if so we can write it as mr times delta r is less than equals to capital MR times delta r. What is the reason behind it? Since delta r is a positive value, right? Since delta r is a positive value, because it is the length of the rth subinterval which the partition has created, right? If so, then we can also take the summation of either of these, and the inequality still holds, right? So you have r equals to 1 to n mr delta r is less than equals to summation r equals to 1 to n capital MR times delta r, and this is the lower Riemann sum of the function over P. This is the upper Riemann sum of the function over P. So this implies LFP is less than equals to U. So this was a very simple proof. The next proof is also very simple. Because it is also we had also discussed this in the previous lecture, that m is less than equals to mr, which is further less than equals to capital MR, which is further less than equals to capital M, where M is the GLB of F in I, in the complete interval, and capital M is the LUB of f in I. Clear? Clear? Got it? So what can we take from here is that so we can multiply delta r on all the sides, so we get m times delta r is less than equals to mr times delta r, which is further less than equals to capital mr times delta r less than equals to m times delta r, and then we take the summation. So m times delta r from r equals to 1 to n, which is less than equals to summation r equals to 1 to n small mr times delta r, further less than equals to summation r equals to 1 to n capital mr times delta r, right? Now since over the complete interval for the function small m and capital M comes out to be constant, so we can take it like this, right? This is the LFP, this is the UFP, and the same thing happens here also. What is summation delta r? B minus a less than equals to LFP less than equals to UFP less than equals to m times s. Okay, so we have proved these two theorems. Clear? Yeah, very simple. The next theorem we have is based on the concept of refinement of partition. The next theorem we have is based on the concept of refinement of partition. So let us see that. Theorem 2, let's say. Under theorem 2 we have, if f is a bounded function on the interval I is equals to closed interval a comma b, and p dash is the refinement of partition P, then point number A, the lower Riemann sum of f over p dash is greater than or equals to that of f over p, and the same thing with the opposite inequality goes for the upper sum. Okay, so the proofs of both these statements are quite same. So we will check the first statement, we will check the proof of the first statement completely, and the second statement I will show you what the changes are going to be. Okay, so let us check the proof. Okay. Achha, before checking going into the proof, let us first discuss what is happening here. Okay, so to discuss that, let us assume that the p is given to be a refinement of p dash is given to be a refinement of p, right? So this implies there exists some element, let's say eta, belonging to p prime, such that eta does not belongs to p. Okay, this is clear. So we take an element in p prime which is not there in p, so this makes p prime a refinement of p given, right? Also by the concept of partition, since both these sets p prime and p are ordered, so there exists element xr minus 1 and xr belonging to p prime such that xr minus 1 and xr belongs to p as well, and xr minus 1 is less than eta, which is less than xr. Clear? So what we mean here is that, suppose we take a number line like this, and this is a equals to x0, this is x1, this is x2, and we keep moving like this, and say suppose here we have xr minus 1, here we have xr, and again we keep moving till you have got xn equals to b. So this is the set of elements we have in P. Okay, we have assumed to be there in P. And when we take the refinement of this partition, there exists one more element eta here. Is it clear? Is it clear? Got it? So it is clearly visible that if we break, if we break the interval into every possible sub-interval, okay, provided taking, the case of the given partition P once and the refinement of P, then we can obviously say that every single interval is intact except this interval, and this complete interval. What I mean by this statement is that, see, okay, if we try to form the sub-intervals, say I prime, okay, I prime, so this is the sub-intervals of I on the basis of P prime. Okay. So this, what are the sub-intervals of the form? So the sub-intervals will be x0 to x1, x1 to x2, and so on till we get xr minus 1 to eta, eta to xr, right, eta to xr, and then it continues again till you have xn minus 1 to xn, right. And what are the sub-intervals of I we have? Suppose I is the sub-intervals of I, sorry, let this be I double prime. I double prime is sub-interval of I on the basis of the given partition P, on the basis of P, okay, the basis of P. So on the basis of P, the sub-intervals will be of the form x0 to x1, x1 to x2, so on, when we reach xr minus 1 to xr till xn minus 1 to xn. So what is happening here is that the only elements which are different in I prime and in I double prime and I prime are x r minus 1 to eta, x r minus 1 to xr, and eta to xr. These are the only sub-intervals which differ between I prime and I double prime. Clear? Got it? Okay. Now keep this in mind. Okay. Keep this in mind. Okay. Now, okay. Now we are coming into the proof. Okay. Let mr prime, mr double prime, and mr be the greatest lower bound of the intervals xr minus 1 to eta, eta to xr, and xr minus 1 to xr respectively. Clear? Respectively. Okay. And from here we can obviously say that mr is less than equals to mr prime and mr is less than equals to mr double prime. Clear? Clear? Because we are taking smaller sections of this itself. We are taking smaller sections of this itself. Basically this and this are sub-intervals of this sub-interval. Clear? Now if we subtract the lower sum of the function f with respect to the refinement partition with LFP, so it is clearly visible that every single value of these two respective lower sums will cancel out except mr prime times xr minus 1, sorry, 1 second, mr prime times eta minus xr minus 1 plus mr double prime xr minus eta minus mr times xr minus xr minus 1. Clear? Because see, in case of the refinement partition, the the value mr times xr minus xr minus 1 will be equal for both the partitions p and p prime for all these subintervals except this subinterval and the whole subinterval, right? Because in these two cases the lengths and the GLBs are different, but for every other subinterval the GLBs are identical as well as the length of the subintervals are identical. Clear? So this is the value which eventually remains when we subtract LFP dash, when we subtract LFP from LFP dash. Clear? Clear? Okay. Now let us do some simple simplifications. So this is xr minus 1 plus mr prime xr minus eta minus, let us write this as xr minus eta plus eta minus xr minus 1, okay, which is, so if we take out these values, okay, if we expand this and we take common xr minus eta and eta minus xr minus 1, what do we get? So we get mr prime minus mr times eta minus xr minus 1 plus mr double prime minus mr times xr minus eta. Now mr double prime minus mr is greater than equals to 0, right? Because mr prime is greater than equals to mr. Clear? And same goes for the other one too. So this implies, and these are the lengths of the subinterval, so these are also positive. So that implies LFP prime minus LFP is greater than equals to 0, which implies LFP prime is greater than equals to LF, and it's proved. Clear? Clear? Okay. Now the proof of the second statement is quite similar to this. The only changes will be, I am just showing you, see, the concept of taking the refinement of partition with one element extra will be same. Okay, we take p prime which is having the value eta which is not present in p, hence the subintervals will be according to what I have shown here. Clear? What happens is that in case of the considering the LUBs, here we have to consider LUBs of these interval, right? So suppose the second statement, so let capital MR prime, capital MR double prime and capital MR be the LUBs of the subinterval xr minus 1 to eta, eta to xr, and xr minus 1 to xr respectively. Clear? And from here it is evident that mr is greater than equals to mr prime and mr is greater than equals to mr double prime. Clear? Clear? Got it? Now what happens is that now if we subtract UFP prime from UFP, what we will be having? So we will be having mr times xr minus xr minus 1 minus mr prime times eta minus xr minus 1 minus mr double prime xr minus eta. Okay, then we break this in the similar form which we have already done to get mr minus mr prime times eta minus xr minus 1 plus mr minus mr double prime times xr minus eta. Clear? Got it? And since this is positive and these two are also positive, so from here we can obviously say that UFP is greater than equals to UFP. Clear? Got it? Got it? Let us check the next theorem. In this lecture we will be considering some theorems related to upper sum and lower sum, because then we will be moving on to what we call lower and upper integral, lower and upper Riemann integral. Okay. The next theorem, let's say Theorem 3. What we have here is that for any two partitions, P1 and P2, LFP1 is always less than equals to UFP2, provided whatever partition they are. Yeah, which can be simplified into a statement that no lower sum can exceed any upper sum. Okay. So how to check this proof? Let's see. Okay. To have this proof, what we need basically is that the concept of the common refinement of two partitions. Okay. The concept of that, 1 minute. Okay. So let's check the proof. So let P star equals to P1 union P2, so it is the common refinement of P1 and P2. Now the above the theorem number 2 which we have on the concept of refinement partition, from there we can write that LFP1 is always less than equals to LFP star, because P star is the refinement of P1, right? We have also studied that the lower sum of any given partition is always less than the upper sum of the function over that partition. So this is statement 1. We also have LFP star is less than equals to UFP star, and since P star is also a refinement of P2, so from the theorem number 2 we can also say UFP star is less than equals to UFP2, right? Because P star is also a refinement of P2. So it is clear from these three statements, from 1, 2 and 3, we have LFP1 is less than equals to UFP. Clear? Got it? Got it? Okay. Let us check the next theorem, the last theorem of this lecture. Okay, let us check it. Okay, Theorem 4, I guess. Theorem 4. Okay, so the theorem says that if P prime is a refinement of P containing small p number of points more than capital P, and fx is a bounded function bounded by k and minus k for all x belongs to interval I is the closed interval a comma b, then point number 1, LFP P is this partition capital P. Okay, LFP is less than equals to LFP prime, which is further less than equals to LFP plus 2 times small p times k times delta, and UFP prime rather UFP, one second, UFP is greater than equals to UFP prime, which is further greater than equals to UFP minus 2 times small p times k times lambda, where the norm of the partition capital P is less than equals to delta, not lambda, sorry, delta. This is delta. Okay, clear? So this is the theorem which we are given. Okay. Let's see. So the initial procedure to prove these statements is quite similar to what we have already done. Okay, that is the theorem number 2. Okay, in theorem number 2 we had considered there is only one particular point eta which is more in P prime than P. Clear? Clear? Now see, for theorem number 2, we had eta belonging to P prime such that eta does not belongs to P. Only one element was there, and we had, and it implied LFP prime minus LFP equals to MR prime minus MR into eta minus XR minus 1 plus MR double prime minus MR times XR minus XR minus eta. Clear? Clear? XR minus eta. Right? Right? Okay. Now see. Now we have fx less than equals to k, which implies minus k is less than equals to fx, which is less than equals to k. Now this implies basically minus k is less than equals to mr, which is further less than equals to mr prime, which is less than equals to k, because mr prime and mr are values of f itself, because they are the GLBs of f in given in certain subinterval, right? And mr is also less than equals to mr prime. We already know it. From here, what we can write? From here we can write mr prime minus mr is less than equals to 2k. Similarly, we can also write mr double prime minus mr is less than equals to 2k itself. So provided these two things, we can say that this implies LFP prime minus LFP is less than equals to 2k times eta minus XR minus 1 plus 2k times XR minus eta, which is equals to 2k times XR minus 1. And since this implies delta R will always be less than equals to the norm of P, and the norm of P is given to be less than equals to delta. So this implies L of P prime, one second. So this implies L of P prime minus L of P FP is less than equals to 2k delta. Clear? Now this happens for only one element in P prime more than P, and if there exists P more points in P prime than P, repeating the same process P times, given P times, that is the number of elements which exceed in p prime than p, we have so this will, this the same process if repeated p times, we have LFP prime minus LFP less than equals to 2k delta times p. As simple as that. As simple as that. Right? Clear? So from here we can say LFP prime is less than equals to LFP plus 2 it is less than equals to 2kp times delta, and we know LFP prime is greater than LFP. So from here we can establish the inequality, which is less than equals to LFP plus 2kp times delta. Is it clear? The same process will happen in the second proof. Second proof is being left as an exercise. Okay, so I'll be meeting you guys